So we're going to use random numbers in our calculator, but your calculator is a computer system and can't actually generate random numbers. If I start doing it, and some of you are all going to get the same numbers, so we have to do something to make sure it doesn't do that. Type in your house number, like 102, whatever it is, plus your age times the number of siblings you have, unless it's 0. Don't multiply by anything. And then hit store. Yeah, hit enter. So then there's a store button that's like right above on. And then hit store math probability, and then the first one, and hit enter. So it's just putting that random number in as your seed number to make you guys have different numbers. So like I just came up with something so that y'all aren't going to get the same numbers. Otherwise, if we didn't do that, all of our calculators start the randomization process at a certain number. All right, so what we are going to do is so what's on your paper? This is a terrible actual example to use on our paper, but it's the only way that I can do something that you can see the whole thing without us writing like 500 different examples. So what's up top is the entire population. So the entire population values are 1 through 7. We're saying that 1 through 4 are considered yellow, and 5 through 7 are considered blue. So at the top of your paper, top on the right, says capital N. What does capital N stand for? Why is it capital and not lowercase? This is for the entire population as opposed to the lowercase. So how many things are in our population? 7. That's what we're right there. We are going to do random samples of size 5. Now, if you really take samples of size 5 out of 7, that's not very helpful, but for the purpose of what we need it, it's fine. So we're going to take samples that are all 5 at a time. We are going to deem success to be yellow. And there are actually 2 sides to this worksheet that both say the same thing, so you're writing it on one. I don't care which one right now. So of that entire population, what is our actual proportion of yellow? 4 out of 7. Let's write that as a decimal too. Which gives me what around the 4 decimals? 0.5714. All right, so that's the actual proportion of our population. But we're going to pretend like we didn't know that. All right, so let's be on the side that says simulating as opposed to considering all possible. So we are going to be simulating random samples from the population. I'm going to show you how to do this in your calculator. So this time, we don't want to be putting them back once we've selected them, at least for this example. Sometimes we will. So if you go to math and over to probability,
Are we using our house number thing for this?
no, we just had to do that once so that your calculators are seated different. So math, probability, and you go down to the bottom, and you see one that says rand int no repeat. Click on that one. How many people's calculator pull up with something other than just that?
Mine said error.
Then you got to clear out, and then like you're in something already. So clear out and go back to it.
Mine says lower.
All right. So those who say lower upper, they say lower upper and what? In.
Wait, what?
Just out of curiosity, they say that all the calculators are supposed to do this, but I don't think it works. Type in 1,7,5. Unless you have one of those, then you're doing 175.
Mine still says error.
Mine won't let me do 1, 7, and 5. But mine didn't work. Did anybody else's work? It did work?
With the lower.
With lower upper, it works.
Wait, what else? Mine still says error.
Yeah, mine.
Yours should say error right now. All right, so let's do. It says we're supposed to have 3 arguments, but I don't understand why because it doesn't work. So be here and just type in 1,7.
But where does it say upper and lower?
Yours doesn't. That's a different calculator. Hey, so once you're there, yours should look like mine is on the board. Rand int no repeat 1,7 and hit enter. And it's going to give you numbers 1 through 7 in a random order. Now, we are only sampling 5. So if you have to do your calculator like I have to on the board, then we're just looking at the first 5. If you have one that does lower, upper, in, then you can do 5 at a time and not have to exclude the last 2. So right here, what are my first 5 numbers? 51427. So on my sheet, where it says values included, don't write anything yet. Where it says values included, I'm going to write in that very first one, what did I say? 51427. So of those, what numbers represent yellow? Anything 1 through 4. So how many do I have? So if I took a sample of 5, what percent of my sample is yellow? Does everybody understand what I did there and how I'm doing it, why I'm doing it? This goes by a lot quicker than I was worried about it going. I want you to, like, these, I wouldn't waste your time to write commas in between them. Just write them all out. Write how many are in each sample and the percent. You might just do these first 2 columns first and then kind of like star or something, which ones are the same. So go ahead and go through this and fill out this whole chart, which is 21 times, of simulating 5 numbers 1 through 7, what they are, and how many of them are yellow.
Is there a way to do it so that we don't have to keep typing?
Yeah, just keep hitting enter. It's going to be a graph. Portion of sample that is yellow. And it's going to be our number of samples. Did I have anybody that had more than 12 of one result? 40, 60, or 80. More than 18 of one result. People who raised your hand for more than 12 of one result, what result was it? Did anybody have more than 12 of a result that was not 60? Okay. So I have 6 tick marks here. If yours is 12 or less, then you can do going by 2s. If yours is more than 12, then you'll probably have to go by 3s. So for my example, the one that I did yesterday when I used my random integer thing on my calculator, is I ended up getting, so my 3 options down here are 40%, 60%, and 80%. Now, eventually these can be like bar graphs, but for right now, I want each sample to be a circle. So for example, I had, in my sample, I had 7 that were 40%. I'm trying my best to space them equally, but be at the right spot and then have them all the same size. So make your graph of dots with your results. It's kind of hard to talk about shape much when it's just 3 possible options here. But we can still get the idea. How many people's, so if you were going to explain what mine looks like without shape words, what are some things you could say? Without saying like symmetric and those kind of words, like just very general. What are some ways you could describe mine?
Most samples were 60% yellow.
Most were in the middle, and then what else? A little bit higher on the left than on the right. How many people did not look anything like that, where it's highest in the middle and a little bit higher on the left than it was on the right?
Mine was a little bit higher on the right than it was on the left.
Did anybody else have anybody that was high more? Anybody else have ones that were more on the right than on the left? So we had 3 people out of 4 people out of 33 that had more on the right than on the left. Did anybody not have 60 be the highest one? What was your, I guess your left one was, oh, your right one was higher. Oh yeah, left one. So is there a little bit of variety? Yes. Is there like extreme variety? So how many samples did we just do? 21. Is 21 that many samples? So should it vary a little bit? I'm not gonna waste time to do all that. If I put all of ours together, I might do that eventually. All right, so now I want to write a title back on this. So this is the estimation of the sampling distribution of p hat. So up until this point in our class, every single thing that we have done has been, hey, I know everything about the population. Now let's make some guesses about our samples, which is not something that really occurs in the real world very much. If you knew everything about the population, why are you doing the sample? So this one, now I told you what the whole population was, but theoretically you could see how if that weren't there and this were on a much bigger scale, we could keep taking samples from the population to guess what the population would look like. Does that make sense? So we were guessing what the population might look like by doing these over and over. We got a little bit of variety, but fairly consistent for the most part for the large chunk of students in here. So now let's. Oh, I want your. I want your estimated mean, but I want to use shortcut stuff to do this so we're not spinning forever. So for my example, go to a list. Oh man. So for mine, my possible values were 0.4, 0.6, 0.8. So everybody's list 1 should be 0.4, 0.6, 0.8. And then list 2 is how many of each one you got. So how do I use that to find the mean of my sample? Stat calc. And then I type in what here? List 1. And then my frequency list is list 2. So for my particular sample, I got a mean of 0.5806. But everybody should not be the exact same. Everybody should vary a little bit. So that first line, 5810 is what I got.
I thought we looked at the summer best for our.
Not when we do it this way.
But yesterday on our test.
What?
Yesterday on our test.
If you did list 1 times list 2, that's when we do the sum.
Okay. Are we doing that right now?
We're letting our calculator do it for us. Like we're not literally typing in list 2. List 3 is list 1 times list 2.
Here, like list 1, list 2, and have it all in the same.
Yeah.
It just does it for you.
That's fine. We can type.
That's why you set the frequency.
Alright, so raise your hand if you got exactly the same mean that I did. Alright, raise your hand if you got lower. Raise your hand if you got higher. Alright, so probably more people higher than lower. What do you think the actual that we should get is?
0.6.
Why?
That was
So the mean of the population actually is 0.5714. So if we do samples and take the mean of those samples, we're hopefully getting close. Is that totally wrong? Like way off? No. Did I do that many samples? No, I did 21. So the more I do this, if it's a good sample, then it's going to get closer to that. So if we probably took all of ours and found the mean of all of our means, we'd probably be really close to what that is. Alright, flip it to the other side. So what we just did is basically said we want to know what the population looks like, but we have no idea what it actually looks like, which is the way it happens most of the time. The side that we are on now, considering all possible outcomes, this is saying if I had every possible way that I could, which means I'm guessing nothing. And this concept is one that gets confused and overlooked, and that's why I'm spending so much time on it. So what we are going to do on this side is figure out every single way that we could get 5 out of that 7 and write them down and find the values for those. So we have how many to choose from? 7. How many are we choosing? 5. Does anybody remember what I can use to figure out how many different combinations there are going to be? And choose 5. So type in 7. Math, NCR, math probability, NCR, and then 5, and hit enter maybe twice, and what do you get? 21, which is why I chose to do 21 on this side, but we didn't understand, like, why did you pick 21 at this point? So there are 21 possible combinations of numbers that I can pick from this. I dealt with this yesterday and I tried to do it a different way and it got really confusing. It's easier to go through and figure out all possible numbers, combinations of two numbers, and then work backwards. So I did 1 and 2, like this is my first column where it says numbers not included. So if I'm doing it this way, what would I go to from there? All the way down to, what's the highest one I can get to? And then I go to what? And then I go to what? And keep going. I don't care if you're talking with people while you're doing this, write those down. And finish it out. So we are writing, so this is your first column, the one that says values not included. This is me writing down every single possible combination of two numbers, 1 to 7, without repeating. No, because you can only pick each number once. So you're taking each value with every value above it, because everything below we've already done. So what's after 34? 35, then 36, 37, then what? 45, 46, 47, then 56, 57, 67 is our last one. So I just went through and wrote down all possible combinations of two numbers, 1 to 7. So it's easier to do it that way, and then now write down what's left. So of my first sample, if those numbers aren't in my sample, what is in my sample?
3, 4, 5, 6, 7.
Why did I choose to write it like that? What are these numbers? What do these numbers represent?
Yeah.
What do these numbers represent? Not yellow. So what would I write with inside this one?
2, 4, 5, 6.
It just made it easier for me when I split it like that, so I was kind of already counting how many yellows as I went. And go ahead and keep writing. So what's the next one? 2, 3, and then 5, 6, 7. So you're writing down all the numbers 1 to 7 that aren't what we wrote down.
But then the one. Even if you're not fully done writing
out the column, you should be able to skip ahead to where we are and be okay with it. Like, you know that you could write down numbers. So how many did we end up with that were 40%? What? How many did we end up that were 40%? 6. How many did we end up that were 60%? How many were 60%? 12. And how many did we end up with that were 80%? So I just spent a lot of time working out the pieces of this because this is a major concept that gets mixed up. What do each of those dots represent? A sample. In this particular case, it represents a what of that sample? Proportion. Later we can deal with the mean of a sample. Does what I had on the back page look terribly, terribly different than what I had on the front page for mine? No. Did anybody's look so ridiculous that they think something is wrong? Later, not in this chapter, but we get to the point where I go, okay, if this is what was supposed to happen, but this is what I got, something's wrong. And that's the next level that we get to. So basically, like if I say, hey, I'm an 80% free throw shooter, and you're like, okay, and you go take me out and I go shoot free throws, and you make this graph of all my free throws, and you're going, yeah, that's not looking like what you said it was going to. Something's wrong here. So that's kind of our next step with using this. The biggest difference between the one we started with and the one we ended with is what were we doing here?
Random.
What?
Random.
Random, and we were making them. Could they have shown up more than once?
Yeah.
Yes. Did we know that these were the exact ones? No. This is an estimation, doing it over and over for what we think it would look like. This one is the truth of what it definitely actually does look like. So you can guarantee the fact that you'll be asked a question, is this the sampling distribution of something? And what they're looking for there is probably no, because we actually did samples. We didn't use every single possible sample of 5 from that entire population that there could be. Does that make sense? Like, that is definitely a question you will see again at least once. The one thing I haven't written here yet is the mean. I can do this since I know y'all can type it in. I'm going back to here. Now we have, how many 0.4s did we have? 6, and then 12 and what? 3? So if I were to do this, what is our mean now? Why does that seem good? If I take all my possible samples and average those together, then I would get what? The exact same thing as the average of all of my individual values. That is a big key thing that I don't have symbols for to tell you yet. But if I used all of them and actually did the true sampling distribution, then the average of those dots should be the exact same as the value for my population. So our actual mean was 0.5714. What, 5714, was that what it was? 14.